To complete our discussion on acid-base equilibria, we're going to talk about the ionic product of water, the base dissociation constants, titration curves, and finally indicators. I'll cover this in 2 videos. Alright, first let's talk about the ionic product of water. In a body of water, we'll have one water molecule acting as an acid and one acting as a base. Remember our definitions. According to Bronsted-Lowry, an acid is a proton donor while a base is a proton acceptor. This can be represented by the equation 2 water molecules goes to form a hydronium ion and a hydroxide ion, but we can simplify this. Remember, the hydronium ion can be simplified to just H+. This equation can be simplified to show essentially that a water molecule is split to form a proton and a hydroxide ion. We can write an equilibrium constant with respect to concentration for this equation. As with all equilibrium constants, it would be the concentration of the products divided by the concentration of the reactant. But a key thing to note is that water is a weak acid and a weak base. So only a small amount of water molecules will ionize, which is why this is a reversible reaction. And the amount that ionizes is so small that it's negligible, and we can accept the concentration of water as a constant. Which is the product of the hydroxide ions and the protons, ionic product of water. The ionic product of water has been experimentally determined to be 1 times 10 to the negative 14 at room temperature. When a water molecule ionizes according to the stoichiometry of this equation, we can see that for every mole of protons that has been produced, we also have 1 mole of hydroxide ions. So that means we have a 1-to-1 ratio. The same amount of both must be present. And with that in mind, we can simplify the expression for the ionic product of water to be AW is equal to the concentration of hydrogen ions squared. Again, that is because the amount of protons and the amount of hydroxide ions must be the same. And if we multiply a number by itself, of course, that means we're squaring it. So the ionic product of water is equal to the concentration of hydrogen ions squared. If we substitute the experimentally determined ionic product of water, which is 1 times 10 to the negative 14, we can actually solve for the concentration of hydrogen. And we would do that by finding the square root of both sides. And the concentration of hydrogen ions would therefore be 1 times 10 to the negative 7. Once we know the concentration of hydrogen ions, we can determine the pH of water. And to find pH, our equation once again is pH is equal to the negative log of the concentration of hydrogen ions. That's negative log of 1 times 10 to the negative 7, which would be 7. This is why at room temperature, the pH of water is considered to be 7. So in any body of water, we would have this equilibrium being set up where water molecules would ionize, and then the ions would combine to reform a water molecule. Now, according to Le Chatelier's principle, if we disrupt this equilibrium, then it's going to cause the position of the equilibrium to shift. So of course, if we change the temperature of water, it's going to cause the position of the equilibrium to shift, and we would end up with a different value for Kw. If we have a different value for Kw, then of course the pH would change. So bear in mind that the pH of water is only 7 at room temperature. Now, why was this important to mention? We have and the relationship between the two is that pH plus pOH is equal to 14. Why 14? Okay, so Kw, the ionic product of water, is 1 times 10 to the negative 14. If we find the negative log of that figure, which is pKw, we would get 14. A strong base. A strong base is any base that would ionize completely in a solution. For example, sodium hydroxide is a strong base, and if we dissolve some sodium hydroxide, we place some sodium hydroxide in water, all molecules of sodium hydroxide would separate to form sodium ions and hydroxide ions. The same would go for barium hydroxide. If we add some barium hydroxide to water, then all the barium hydroxide molecules that dissolve would separate to form barium ions and hydroxide ions. Because they ionize completely, then we can use the concentration of the sodium hydroxide solution to know the concentration of the hydroxide ions. So if we had 0.1 mole per dm cube sodium hydroxide, then that means we must also have 0.1 moles of hydroxide ions. If we had 0.05 moles of sodium hydroxide, that means we also have 0.05 moles of hydroxide ions, because every single sodium hydroxide molecule would separate to form hydroxide ions. So any amount of sodium hydroxide we had, the same amount of hydroxide would be present. How do we go about finding the concentration of a solution, of a basic solution? Another definition of base is the Arrhenius definition, which speaks to the presence of hydroxide ions. It's actually what we are going to work with in these equations. If we wish to find the pH of a strong base, we have to think about the relationship pH plus pOH is equal to 14. So we have to find pOH. In all of these calculations, the P means exactly the same. P is negative log. That's what we're going to be putting in our calculator anytime we see a P, negative log. And because this is a strong base, and because barium hydroxide is a strong base, and this barium hydroxide had a solution, and this barium hydroxide had a concentration, so we have to find pOH. In all of these calculations, the P means exactly the same. P is negative log. That's what we're going to be putting in our calculator anytime we see a P, negative log. Because barium hydroxide is a strong base and this barium hydroxide had a solution, and we would determine the pOH, substitute it in the equation, and then solve to find the pH of this barium hydroxide solution. But what if we had a weak base? Weak base is only partially ionized. An example of a weak base is ammonia. If ammonia is added to water, it will ionize to form the ammonium ion and the hydroxide ion. But these ions, once formed, will recombine and form ammonia and water. This means we have a reversible reaction, and with all reversible reactions, we will have an equilibrium being set up. So whenever we're writing our expression for our base dissociation constant, just bear in mind that we're not going to include water in our expression. Water has a constant concentration, or close enough to constant for us to ignore it. Let's look at an example. This question says a 0.025 mole per dm cube solution of hydroxylamine has a pH of 9.11. What is the value of Kb for this weak base? Hydroxylamine has the formula NH2OH. I'm going to detour for a bit to show you why amines, any amine can act as bases. Now, amines are compounds, usually organic compounds as well, that contain an NH2 group. So whenever we have an amine or ammonia, amines are derived from ammonia. Whenever we have an amine and it's acting as a base, it means that this amine is going to gain a hydrogen, and that hydrogen is always added to the nitrogen. Because this hydrogen is a proton, then of course protons have a positive charge, which means that this compound also has a positive charge. So what we will form is NH3OH plus OH minus. So from this H2O, one hydrogen is donated to hydroxylamine, and the remainder of the water would be OH. We can write our expression for Kb. Kb would be the concentration of the products divided by the concentration of our reactant. Remember, water is not included. We have removed it. It's a constant, and that's why we even have that Kb expression. We'll be able to tell exactly how much hydroxide ions are present. But we can't do the same when we have a weak base because it only partially ionizes. Some OH will be present, but some of the compound will remain. So in this case, we're going to have some hydroxyl and we're going to have some hydroxylamine that didn't ionize. And because it is, we're going to have some hydroxylamine that didn't ionize. Which means that we know the concentration of the hydroxylamine, but now we need to find out the concentration of the hydroxide ions. Based on our balanced equation, for every single mole of hydroxide ions that are formed, we can see that the same amount of the amide ions, hydroxylamide ions, will be formed because we have a 1-to-1 ratio. And what that tells us is that from our expression, we're going to be multiplying the same two numbers right there. We're going to be multiplying a number by itself. And for that reason, we can simplify it to be OH, the concentration of the hydroxide ion squared. So here's our simplified expression. pH plus POH is equal to 14. That means POH is equal to 14 minus 9.11 is equal to 4.89. And the POH, since we know that POH is the log of OH, the negative log of OH, to find the concentration of OH, that will be antilog negative 4.89. That would be 1.29 times 10 to the negative 5. That would be equal to 6.656 times 10 to the negative 9. The units for this equilibrium constant would be mole per dm cubed. Acid-base equilibria, we would have met two new equilibrium constants. We met Ka, which is our acid dissociation constant, and Kb, which is our base dissociation constant. Remember, in both cases, we would, and with all equilibrium constants, we would divide the concentration of the products by the concentration of the reactants. Products would be where we have our ions, and the reactant would be the compound that we start with. In order for us to have a strong acid, it means that we must have just ions being left back. So all the compounds would have separated and would just have ions. The same would happen for base. We would only have the ions being present. So The value that we get for Ka or Kb can tell us how strong of an acid or base we have. If we have a larger numerator than denominator, then we're going to have a high value for Ka or Kb. The higher Ka is, the stronger the acid is, because it means we'll have more ions being present, more protons being present. The same would apply for Kb. The higher Kb is, the stronger the base. But we only have Ka or Kb when we have weak acids and weak bases. So we always end up with an exponent. So we're going to have the figure times 10 to the negative 9, or 10 to the negative 14, or 10 to the negative 16. We always have this exponent to work with. And that was the importance of finding the negative log of these numbers. It gives us smaller numbers to compare. So two other terms that you should be familiar with are pKa and pKb. If we find the negative log of Ka, we get our pKa, and the lower that value is, the stronger the acid is. And the exact same applies for pKb. If we find the negative log of Kb, then we have our pKb, and the lower the value of pKb, the stronger the base. So this is for comparison purposes. If you were supposed to compare base A to base B, you can look at the two Kb values. Whichever one is higher is the stronger base, or we can look at the two pKb values. The one that is lower is the stronger base.